Alright, so in this video I'm gonna be explaining another important paper with the title LSEnet, Lorentz Structural Entropy Neural Network for Deep Graph Clustering. This paper in ICML 2024. Graph clustering is a fundamental problem in machine learning. Deep learning methods achieved the state-of-the-art results in recent years, but they still cannot work without predefined cluster numbers. Such limitation motivates us to pose a more challenging problem of graph clustering with a known cluster number. We propose to address this problem from a fresh perspective of graph information theory, for example, structural information. In the literature, structural information has not yet been introduced to deep clustering, and its classic definition falls short of discrete formulation and modeling node features. So they formulate a differentiable structural information, DSI, in the continuous realm, accompanied by several theoretical results. By minimizing this differentiable structural information, we construct the optimal partitioning tree where densely connected nodes in the graph tend to have the same assignment, revealing the cluster structure. So densely connected nodes, we pick them together. DSI is also theoretically presented as a new graph clustering objective, not requiring the predefined cluster number. Information entropy is a key notation of information theory, measuring the amount of information of unstructured data, and it fails to study the information on graphs. On information measure for graphs, for example, von Neumann entropy, Gibbs entropy, are still defined by unstructured probability distribution, and the graph structure is degenerate. But recently, the structural entropy is proposed in this paper for graphs. And they define h-dimensional structural entropy in this paper, Lee 2016, that it shows that the structural information of this graph G with respect to each non-root node alpha is here. So this alpha is associated with a subset of V denoted as module T sub alpha. And the immediate predecessor of it is called alpha minus. The module of the leaf node is a singleton of graph node. The scalar is the total weight of graph edges with exactly one endpoint in module T sub alpha. So h-dimensional structural information of G is given here, traversing all possible partitioning trees of G with height h. H-dimensional structural entropy of G is defined like this. The structural information in this equation is formulated node-wisely and cannot be optimized via gradient-based methods. So to bridge this gap, we present a new formulation of structural information with the level-wise assignment, which is shown to be equivalent to the classic formulation. This is the level-wise assignment, that for a partitioning tree with height h, assuming the number of tree nodes at the edges level is n sub h, we define level-wise parent assignment matrix. They also define h-dimensional structural information. So we have a partitioning tree T. We rewrite the formula that I said with respect to T as at height h. And V is the volume. This is the volume of your graph. And for graph node sets T sub k and T sub k minus, we have the corresponding case node H. We have these volume of graph nodes. And then they have a theorem that says this formula for HT is equivalent to T in definition 4.1. So they are equivalent. But what are the properties of them? First, additivity, which is proved in the appendix of this paper. The one-dimensional structure entropy can be decomposed. So it is additive. It can be decomposed like this. And this E here is just the entropy. So how is it related to graph clustering? Because we have got a lower bound. So the normalized H structural entropy, so this is the entropy, this tau is the entropy, this ratio, and phi is the conductance. So the lower bound of entropy is our conductance, and this is the main idea of this paper. So we consider differentiable structural information by minimizing this entropy. And so what is LSEnet? It's a Lorentz structural entropy neural net which aims to learn optimal partitioning tree in the Lorentz model of hyperbolic space. So we design a Lorentz convolution layer to learn leaf embedding in the hyperbolic space, where x sub I and z sub I are node feature and leaf embedding respectively. In the partitioning tree of height h, the level of nodes is denoted by a superscript of h, and we have h from 0 to h, from leaf nodes to root. And we adopt attention aggregation and specify the aggregations like this. First dimension transform is done via Lorentz linear operator, and the linear operator is here. So H is the neural network, W and V are parameters. Second, we derive attentional weights from self-attention mechanism. The attention weight between nodes I and J is calculated like this. This is the attention. So this is query, this is the key, and so we calculate the attention weight between nodes I and J. The queries and the keys are derived from node feature via L linear with different parameters. So given a set of points, x sub I, the Lorentz model, here omega is just, this one is the weight vector, and x are summarized in x, all of them, in the capital X. The augmented form is this capital omega, and we have L aggregation is just a transpose of this vector. So this is called the convolution layer of that. And we have Hadamard product with A. So this is the overall structure of LSEnet, that we encode G into Lorentz model and recursively utilize Lorentz assigner and geometric centroid to construct a tree from down to top. Of course, this may not be biologically inspired. So the Lorentz assigner is here. So the real magic of clustering is in this equation 17. So the intuition is that neighborhood nodes in the graph tend to have similar assignments. And then here they talk about the complexity of this. So they did experiments on some datasets like Sightseer and Cora, and they compared with something very easy like k-means. So what is the performance k-means compared to these methods? And the measures are NMI and ARI. Again, measures are NMI and ARI for different data sets. And this is the pseudocode for decoding a partitioning tree from hyperbolic embedding in BFS manner, breadth first search. This is the visualization of hyperbolic partitioning tree of Cora dataset.